Today we are going to learn about demystifying PCA, step-by-step implementation in Python. You'll gain skills in implementing PCA using Python for dimensionality reduction and data visualization. Welcome to our video on demystifying PCA, step-by-step implementation in Python. Principal Component Analysis, or PCA, is a powerful statistical technique used to simplify complex datasets. It's crucial for dimensionality reduction, which helps in enhancing computational efficiency and data visualization. Throughout this video, we'll guide you through implementing PCA using Python, step by step. By the end, you'll be equipped to perform PCA on your own datasets, gaining insights and improving computational efficiency. Let's dive into the world of PCA and unlock its potential in data analysis. Before we start coding, let's understand the basics of PCA. PCA stands for Principal Component Analysis. It's a method used to emphasize variation and bring out strong patterns in a dataset. The main idea is to reduce the dimensionality of a dataset while retaining as much information as possible. This is achieved by transforming the data into a new set of variables, the principal components, which are orthogonal and uncorrelated. PCA is beneficial because it reduces the complexity of datasets, making it easier to visualize and analyze. It's widely used in areas like finance, bioinformatics, and image processing. In data science, PCA is crucial for pre-processing data, especially when dealing with high-dimensional datasets. By the end of this video, you'll be able to apply PCA to your datasets, improving both your analysis and efficiency. To implement PCA in Python, we need a suitable programming environment. Let's set up our Python environment. We'll primarily use libraries like NumPy and Pandas for handling data, and Sklern for implementing PCA. First, ensure you have Python installed on your system. Next, we'll set up a virtual environment to manage our project dependencies. You can create one using the command python env PCA_env. After activating the environment, install the required libraries using pip install numpy pandas scikit-learn matplotlib seaborn. Jupyter Notebook is highly recommended for this tutorial because it allows you to write and execute code in a more interactive format. Install it using pip install jupyterlab. Once everything is set, launch Jupyter Notebook by typing jupyterlab in your terminal. This setup will provide the tools needed to perform PCA on any dataset efficiently.
With our environment ready, let's load and prepare a sample dataset. For this tutorial, we'll use the iris dataset, a classic dataset in data science. It's readily available in the Sklern library. Start by importing the necessary libraries. Import pandas as PD and from sklern.datasets import load_iris. Load the dataset using iris equals load_iris and convert it into a pandas data frame for easier manipulation. df equals pd.dataframe data equals iris.data, columns equals iris.feature_names. Before applying PCA, ensure the data is clean. Check for missing values using df.icenull. Sum. If there are any, decide whether to fill them, remove them, or drop the affected rows. For PCA, the data should be standardized. This means scaling the data so that each feature has a mean of 0 and a variance of 1, which can be done using Sklern's standard scaler. Preparing your data properly ensures that PCA can be applied effectively, providing meaningful results.
Before diving into PCA, it's essential to understand the concepts of covariance and correlation matrices. Covariance measures how much two random variables vary together, while correlation measures the strength and direction of a linear relationship between two variables. In PCA, the covariance matrix plays a crucial role. It helps us understand the spread and direction of the data. The covariance matrix is calculated by finding the covariance between each pair of features in the dataset, which results in a square matrix. On the other hand, the correlation matrix is a normalized version of the covariance matrix that only takes values between -1 and 1. While both matrices provide valuable insights, PCA primarily uses covariance matrices to identify the directions, or principal components, in which the data varies the most. Understanding these matrices is key to grasping how PCA reduces dimensionality and identifies patterns in data. One of the central steps in PCA is calculating eigenvectors and eigenvalues. These mathematical concepts are fundamental for understanding how PCA works. Eigenvectors are directions in which a particular linear transformation acts by compressing, stretching, or flipping. Eigenvalues correspond to the factor by which the associated eigenvector is scaled. In PCA, eigenvectors represent the principal components, and eigenvalues indicate the magnitude of variance captured by each principal component. To calculate these, we use the covariance matrix of the dataset. In Python, we can use the numpy.lineage.eig function to compute them. This step is crucial because it helps identify the principal components that capture the most variance in the dataset. The principal components are ordered by their eigenvalues, with higher eigenvalues corresponding to components with more significant variance. Understanding and interpreting these values allow us to effectively reduce the dimensionality of our dataset while retaining most of its information.
Once we have our eigenvectors and eigenvalues, we can transform our data using the PCA components. This process involves projecting the original data onto the new feature space defined by the principal components. Start by selecting the top principal components based on their eigenvalues. These components capture the most variance. In Python, this can be done using the PCA class from Sklern. From sklern.decomposition import PCA. Instantiate the PCA object with the desired number of components. PCA equals PCA, n_components equals 2. Fit and transform the data using x_PCA equals PCA.fit_transform scaled_data, where scaled_data is your standardized dataset. This transformation reduces the dataset's dimensionality while preserving as much variance as possible. The transformed data can now be used for further analysis or visualization. This step is crucial because it allows us to work with a simplified version of the data, making it easier to analyze patterns and relationships.
After transforming the data with PCA, the next step is interpreting the results and visualizing the components. The PCA output includes the transformed data, the explained variance ratio, and the principal components themselves. The explained variance ratio indicates the proportion of the dataset's variance captured by each principal component. It's crucial for understanding the effectiveness of the dimensionality reduction. Visualization helps in interpreting these results. Use matplotlib and seaborn to create scatter plots of the PCA components. Import matplotlib.pyplot as PLT and import seaborn as SNS. Plot the first two principal components to visualize the data in reduced dimensions using SNS.scatterplot. This visualization reveals patterns, clusters, or anomalies that were not apparent in the original high-dimensional data. Interpreting these results helps in making informed decisions and gaining insights from complex datasets.
A critical aspect of applying PCA is selecting the appropriate number of components. This decision impacts the balance between retaining information and reducing dimensionality. One approach is to consider the explained variance ratio. It indicates the proportion of variance captured by each component. A cumulative variance plot helps visualize this, allowing you to choose the number of components that capture a significant amount of variance, typically 95% or higher. The goal is to retain enough components to capture the dataset's essential patterns while simplifying the dataset. Balance is key. Too many components defeat the purpose of dimensionality reduction, while too few may lose critical information. Experiment with different numbers of components and evaluate their impact on your analysis. This trial and error approach helps find the optimal number of components for your specific dataset and analysis goals. Congratulations on completing this tutorial on demystifying PCA, step-by-step implementation in Python. We've covered the essential steps, from understanding PCA basics to implementing and interpreting PCA results. PCA is a powerful tool in data science, offering a way to simplify and analyze complex datasets. Understanding PCA empowers you to enhance your data analysis, improve computational efficiency, and gain insights from your data. We encourage you to practice these steps on your datasets and explore further applications. PCA has vast potential in fields like finance, bioinformatics, and image processing. For those interested in deepening their knowledge, numerous resources and courses are available online. Keep experimenting, stay curious, and continue learning. Thank you for joining us, and happy analyzing.